Howdy, my name is Louis Rufino, and this is mine and my teammate Devin Kelly's Data Analytics in Cybersecurity final project, the application of ensemble models in bot detection. I will be starting this presentation, and Devin will pick up halfway and conclude the presentation. So, on social media, there are millions upon millions of posts per day across numerous sites. On the website, formerly known as Twitter, there are around 500 million posts per day. While a large majority of these posts are from real, active users, there exists a substantial amount of fraudulent accounts known as bots. Bots are accounts run by various automated scripts and programs, hence the name, that post for some ulterior motive other than engaging with their friends. This could be to cause a disruption, spread fake news, influence culture, harass people, or spread malicious links. A bot account can originate in several different ways. This includes starting as a fully fledged bot, or possibly by taking over a real account. For example, some users may abandon their account and let it fall into dormancy, allowing a bad actor to gain access to it and leverage the real data already existing on the account to hide itself. Sometimes I'll see an account on Twitter that looks fishy, and when I click on it to investigate, I find the profile went from one day posting about their favorite music or movie to suddenly only posting Temu ads. An account doesn't even need to be dormant for this to happen. Sometimes an account is hijacked through phishing attempts on the real user. Regardless, bots pose a real problem for sites because at best, they muddy the user experience, and at worst, can make a site completely unusable. This has led to many groups, internal and external to these social media sites, to research ways to reduce bot accounts online. The problem with trying to get rid of bots is that while some are blatant, others are more sophisticated and take steps to blend in. This could mean hijacking a real account, like I just talked about, or faking interactions with other bots or real users to seem more real. Furthermore, unfortunately some users just act like bots and could exhibit all the usual signs of being a bot, but be a real-life user. All these things combined makes it extremely difficult and tedious to manually flag accounts as bots. As if trying to catch bots was difficult enough, there are huge consequences for not approaching this problem correctly and methodically. If you're too strict, then you run the risk of flagging real users as bots, making them upset and more likely to leave your platform since they can't use it anyways. Though, if you're not strict enough, you run the risk of not catching an impactful number of bots and having your site overwhelmed with them, which will also result in your users leaving. So instead of starting with flagging an entire account, instead, a site may opt to only flag posts. What difference would flagging a post versus flagging an entire account do? Well, for starters, there's a much lower consequence for false positives. Having a post taken down for suspected bot behavior is less upsetting for a user than having their account taken down and having to ask for a manual review. The user is also free to continue posting and using the site if just their post is mistakenly flagged. Furthermore, analyzing posts is much less computationally expensive. When considering a profile, you have to look at several posts, current user behavior, past user behavior, and potentially interactions in order to make a worthwhile determination. You can still apply these criteria to an individual post, but because the consequences are not as steep if you're wrong, and since you have to, at minimum, consider the single post, it's much simpler. Since we touched on computational expense, I'll go ahead and say that obviously one of the best ways to handle bots is to leverage AI and machine learning. These tools are able to go through exponentially more data than a human and can make quick decisions en masse. making it essentially perfect for this job. Additionally, these tools can quickly adapt to new trends in bot accounts and be applied in different ways. While there are a host of very complex applications of machine learning, like neural networks, our project focused on the use of more traditional machine learning models. We chose to use binary classifiers like random forest, ridge, support vector machines, and logistic regression. These models rely on feature extraction in order to classify something as one thing or another, in this case, bot or not bot. These features can be things like sentiment analysis, where the text is processed in such a way that the model determines the emotional tone or opinion of what it's looking at. Or term frequency inverse document frequency, where a model finds out how important a word or series of words are in a text compared to a collection of texts. For our project, we focused on term frequency inverse document frequency to attempt to determine text that appears frequently in bot posts, but not real user posts, and then use that to make a decision about the legitimacy of an account in general. I'll now pass the presentation over to Devin.
Howdy. So the data we used is from S. Cresci et al., and this has over 8 million tweets from over 3,000 genuine users, and just under 10 million bot tweets from thousands of bot accounts. And these are from all different types of bots. You have traditional bots that are just trying to get you to buy something, click on a malicious link to steal your information. You have social spam bots that are trying to spread bogus news or try and rile people up. You also have fake followers that are that people pay for to inflate their own profiles, make them look like they have more followers, more likes than they really do, try and boost their engagement artificially. And this dataset covers all of them. And I believe this is why it is frequently used in peer-reviewed experiments. A lot of the papers we were looking at in our literature review had this data set focus in particular, and it is a very robust data set that's used frequently. Although it is from 2017, a lot of the information there you can still see in bots to this day. Now, for how we actually ran our experiment. Of course, we had a training, testing, and validation data splits, so that way we could actually train up models and then compare them with each other without poisoning the final results by sharing the test data set too early. And we trained a whole bunch of individual models. In particular, we had 3 support vector classifiers. We had radial basis function, we had polynomial, and we had sigmoid kernels. That way we could just see how it performs on all those different shapes of functions. And instead of just saying that one model was more than accurate than the other, we actually looked further into them once we got our confusion matrices. We took all the incorrectly classified data and tried to find the overlaps between different models. So we would look and say, does this one model misclassify the same thing as the other one? That way we can try and pair up the ones that misclassify different things in order to try and get a better idea of how we can actually better ourselves when we are creating our ensemble model. Once we had all that information, we could actually start building our ensemble models and comparing them to the individual models. We built 4 in particular. I'll cover those later. But we would actually compare those to each other and look at the raw metrics from all those to see which ones actually perform best. In our experiment, in particular, we were prioritizing a low false positive rate since we determined that it would likely be a lesser cost to companies, because a false positive on a social network may lose you some users who are angry that their posts are getting taken down, whereas false negatives, if there's still a bot that gets through, there's other reporting mechanisms. You can manually report posts as spam. You can have other things come in and kind of join up to say, hey, this may be a spam account because of other information, maybe from a Twitter bot account detection algorithm, rather than just the post one alone. And then we would actually subject the best ensemble to the final data set to ensure that the actual metrics do hold up across the validation data set, and that we won't see a significant drop off in our statistics once we pump it over to a new data set that it hasn't seen before. And so for actual results, the ridge classifier performed as the best individual model. It had very few false positives and only a handful of false negatives. Logistic regression had a handful more false positives and about half the false negatives, but I consider the ridge classifier to be better still because although it is only 7 more incorrectly classified on the false positive category, if you extrapolate that out to the 500 million tweets made per day, it becomes a heftier number than what was represented here. Because there was about 100,000 in the test data set. So if you extrapolate that out, that's not just 8, that is a whole lot more, and that becomes a larger issue for manual intervention. What we did find, however, is that random forest covers incorrectly classified cases from logistic regression. So a lot of the ones that logistic regression was misclassifying, the random forest classifier was missing entirely different ones altogether. And so we determined from that that they would be a good pair together. Because of that, we built 4 ensemble classifiers. We built the ridge classifier, partnered up with the logistic regression because we wanted to pair our top 2 together to see how they did alone. Then we made another that was the same thing, but we threw in the random forest as well, since logistic regression and random forest work really nicely together. We put support vector classifier with logistic regression and random forest because I wanted to keep the logistic regression and random forest together because they paired so well, and give a support vector classifier a shot to see if it would actually help anything. Because as we can see from our data, support vector classifier, no matter which kernel we used, it did not perform all that well. It was labeling every post as bot made. And for our final ensemble, we did just logistic regression and random forest alone, because again, they paired well in the data sets. Wanted to see how they performed on their own in joint. And what we saw from the data was that the ensemble that included ridge regression, logistic regression, and random forest performed the best. It only missed 1 and had less false negatives than just ridge regression and logistic regression alone. And so when we put that into the final testing data set, we saw roughly the same results. It got 1 more incorrect for false positive and only a handful more false negatives. So we consider this to be a success, showing that this model actually does work once extrapolated to data it hasn't seen before. And our conclusion from this is that ensemble of traditional machine learning models can actually outperform its components at a very low computational overhead. It didn't take too much longer for us to train up the ensemble models than it did the individual models themselves. And with them being traditional machine learning models, they don't have too much overhead to begin with, especially compared to some of the larger models we're starting to see now, especially once you get into neural networks and transformer models. These have a significant low training time with less than an hour overall on relatively non-commercial hardware. And with the accuracy we were seeing of basically 100% with a few misses here and there, we think that this is accurate enough for a potential real-world application. Because as I was saying earlier, we didn't have all that many false negatives, so that's not too many spam bots actually getting through our filter, and very, very little false positives, meaning that a lot of users are not going to get falsely classified as being a bot. However, with this dataset being as old as 2017, it would be nice to actually see a newer dataset to prove that this is more representative of real-world data before we would vote for having it be applied in a real-world environment. As for other future work, we could include neural networks into the ensemble. As been specified, this one only focused in on traditional machine learning components. So we could also consider a convolutional neural network, a deep neural network, and some transformer models thrown into the ensemble. Some of the other papers we saw were using BER, we were using convolutional networks, we were using artificial neural networks, and a handful of others. It'd be interesting to see how those actually perform when thrown into our ensemble models, and if they would pair well with random forest and the logistic regression, or if they would pair well with the ridge regression, and how many of the traditional models they would need to actually see a performance gain significant enough to make it worthwhile. We could also look into enhanced feature extraction. One thing we could do is actually apply more to it. a lot of bots will talk in code and have special symbols and replacing characters to bypass basic word filters. So instead of link in bio, you may see link in bio with a 0 instead of an O. And we can actually have data, we can actually go in and look at the data and try and decode all those and restore them back to what they originally are. That way our TF-IDF can actually go in and match them up as what they are. There's more stuff past that. You can have further feature extraction from more sentiment analysis models. You can actually go into the links that were shared. We convert them down to their host names in our actual experiment instead of just having it be the full link itself. But it would also be possible to convert all those links into some kind of summary of what's on the page itself. One final thing is that it could encompass multiple languages. Our data set was all in English, and so it would be nice to see how this model performs in other languages. Here are our references. Thank you so much for listening to our presentation. Thanks and gig 'em.